Hi again, friends of visual shaders. Maybe you remember that in previous videos that dealt with this topic, we are working only with fragments and we were setting only the final color for pixels. This time, we'll finally get to a no less important function, which is responsible for modifying vertices and subsequently deforming the entire texture that the shader is applied to. As an example, I chose the implementation of a flag that ripples in the wind. This time, we won't be working with the entire screen because we can assume that the flag won't cover the full viewport, and in addition, we'll want to have several instances of flags in the scene with different parameters. So we'll start with a new scene based on Polygon 2D. I'll right-click the scenes folder, create new scene, and it will be a specific node which I will set to Polygon 2D. And the scene name, let's call it flag. Okay. Where is it? Here. So I will find a material, and material is new shader material. Click and select shader, new shader, make sure it's visual shader and canvas item, and I will call it, for example, ripples, and put it to the shaders folder. Okay, and let me click the root node, and now we need to add a texture because the flag should have some kind of picture to wave, and I prepared something here. It's just a screen from one of our previous videos. Let's use this as a temporary flag. There it goes. Nothing is visible here yet because we need to create a polygon first. So to make it easier, I'll just activate the snap to grid. And now let's click here, create points, and just estimate the basic rectangle shape. We will fix it later. 1, 2, 3, 4, and back to this. Yeah, something is visible here, but we need to adjust that to the actual coordinates, actual size of the texture, which is 1280 by 720. So I will open data here, Polygon, and fix it. 00 is correct. This is right. No, it's not. It should be 1280. Okay. Now 1280 by 720, and finally 720. All right, this is correct. Yes. By the way, why Polygon 2D? We would like to work with vertices, and if we apply the shader to a regular Sprites 2D or ColorRect, we would only have vertices at the corners, just 4 of them. This wouldn't allow us to achieve the transformations we want, so we just created a basic polygon, and now we'll add inner vertices to achieve the waving effect. I will place the individual points and adjust their coordinates in the inspector, as I'll often won't be able to hit them accurately with the mouse. For the basic effect, it should be sufficient to divide the upper and lower sides of the texture into halves, then quarters, and then eighths. This may take a while, but fortunately we'll only need to do this preparation once, and later we can duplicate the scene for flags of different sizes and types. So this time I will click here, edit points, and use the left mouse button to add more vertices. Here at the half, then quarters, and the eighths. 1, 2, 3, 4, and the same at the bottom side. Half, quarters. There are of course some inaccuracies, but it's not too important because it will be very visible at the flag animation. Okay, let's say this is finished. The polygon should be ready, so it's time to start working on the shader. I will click the shader property to open the visual shader editor. First, we need to set the input parameters to uniforms. We will have a total of 4. I will start with a speed parameter of the type float because we want to control the speed of the wave effect. Right click and parameter, it would be float parameter. Let's call it speed, and the hint would be, let's say, range plus step, so from 0.5 to, for example, 5, and the step 0.1. Okay, let's define the initial value, that would be 2. Very well, I think we'll need a lot of space here, so I'll just move these nodes over there. And now we need to set up the amplitude and frequency of the waves, because we'll be using a periodic function, most likely sine or cosine. And as we know, this function can have different amplitudes, which is basically the height of this sine wave, and the frequency, which is how quickly the values alternate from -1 to 1. I will make these as vectors too, because we want to set the amplitude and frequency for both x and y coordinate. Right click, and it would be a vector2 parameter. There it is. Let's call the first one amplitude. And the default value would be 25 and 50. This is just a result of my previous experiments, so you can of course put different values and do your own experiments. And Ctrl D to duplicate, and this copy would be called frequency, and the default value I'll set to 5 and 5. Okay, let me just use this trick and expand that so we have a better overview of the whole graph. Now, our goal is to periodically modify the x and y position of each vertex based on their coordinates. To achieve this, we will need time, which we will input as a time node. So let's do it. Right click and time. Okay. Then UV coordinates. Right click, add the node UV. Fine. And finally, some periodic function. As you probably suspect, and I already suggested, trigonometric functions will be the most suitable for this purpose. So I will prepare, right click here, sine of, probably not float, it will be working with vectors, but you can change it later, sine. All right. Now we need to create the argument for the sine function. It will consist of both a time component and to make the vertex move and the coordinates of the vertex. We'll start with time, which we'll multiply by the input parameter speed, so that we can control the speed of the flux wave. Right click, add node, float operation, which will be not add but multiply, and let's connect time multiplied by speed. Very well. Now we will add the UV node and we'll add its y component to this previous result. We do this because we want to shift the phase of the sine wave depending on how high the current point is, so that the vertical edge waves nicely. So we will expand this to get both components of the UV. Red and green is basically x and y in this context. So I'll add another float up, and this time we will have addition and connect the y component here to this result. Good. So now I can connect the result of this sum to the sine node as its argument. Excellent. However, this is not enough. As we know, the sine produces values from from -1 to 1, so such a small vertex shift would be practically invisible. It's time to add the x component of the amplitude to the calculation. We'll perform a vector decompose first and to get the x-coordinate and multiply the sine by the amplitude. Right-click, vector decompose, vector 2, let's connect the amplitude and take the x-coordinate, and as I said, we will multiply the sine result. So let's just put it here, add node float up, multiply result of the sine and the amplitude. Right, vector 3 is incorrect, vector 2 of course. Very well. At the beginning I mentioned that sorry. At the beginning I mentioned that we need to change the vertex position, so we first need to know its initial value. I will add another input node for the vertex and add our previous calculation to its x component. Right click, vertex, there it is. Let's expand to get x and y coordinate. And as I said, we will add it because we want just to shift the vertex, not to calculate a new value just out of blue. Right click, add node, again float up. Let's keep it as add, and to the x coordinate we will add this. However, the result is a float and we need a vector that can be connected to this vertex output. So this time we will use a vector compose. Right click, vector compose for vector 2, as we are in 2 dimensions, and we will connect this result as the x-coordinate, and the y-coordinate should stay as its initial value of the vertex. So we will only connect this green to y, and we have it here. We can connect the result to vertex output. Let me check the result. So click here and put it down. Yeah, something is happening. We have some waving going on. However, it's not quite right because the flag should remain stationary at the on the left side, where we assume the pole is. The solution is simple. We will multiply the previous calculation by the x-coordinate of the vertex, which is 0 on the left and increases as we move to the right. So to keep the graph from getting too messy, I'll just duplicate, I'll duplicate this UV node and connect it to the multiplication operation. I'll click the UV node, Ctrl D to duplicate, I'll move it here, and as I said, we want to multiply it by this value, so let's add another float up, which would be a multiplication, and x-coordinate, let's connect here, and this one would be connected there, and the result, let's move it, too many nodes here already, let's move it here and check the result. Yeah, it is correct. Can you see it? Stationary here, waving over there. Great. That should give us a horizontal waving. However, we've forgotten something, as the frequency. Frequency is not included in the calculation, so the wave effect is very slow. Let's add a new vector decompose and connect the x component to the multiplication of the sine argument. Let's do it here. Just Ctrl D to duplicate this. I'll connect frequency and the x-coordinate. So this is the argument of the sine function, and we want to multiply it by the frequency before applying. So let me add another float up, that is multiply. I will connect the x-coordinate, x component of the frequency, and this part, and now we can reconnect here. Let's check it. Yeah, it's faster, and once we get to the uniform parameters at the inspector, we'll be able to change it using the frequency argument. Nice. Very well. Now we can use the same process to modify the vertex along the y-axis. We can reuse time and speed and UV here, so all we need to do here is to duplicate this float up, and we'll be adding the x coordinates to the formula now. 1 and 2. Okay, let's just put it here to be better visible. And again, we want to multiply this result by the frequency. So I will duplicate this node, put it here, and it should be, this is the first argument, and the frequency of the y coordinates is used here. All right. And we will add another sine function to be applied on the result. And we need to multiply that by amplitude and y component of the amplitude. Let's duplicate here. Float function is the first argument, and the amplitude of y is the second one. And multiplication by the UV coordinate, Control D. So this one and this one, yeah, I am reusing the x coordinate because to achieve the consistent wave effect, we want to do it the same way in both x and y. Okay, and finally, it should be added to the y coordinate of the vertex. This is this operation. Let's duplicate that, move it here, connect, and let's get rid of this green thing because we'll connect it here and connect the result over there. Let's check the flag now. So click here, and yeah, it's waving in both directions. By the way, we can see that the corners of the flag appear to be circling, which looks a bit unnatural. So we'll improve their movement by shifting the face and changing the sign to cosine for the x coordinate. Let's find it, it's here, sine to cosine. Okay, that's better. Of course, you can add vertices on the vertical side as well to create a denser mesh to make the flag waving smoother. It depends on the specific use case. However, the principle remains the same. There is one last thing left. Flagpoles, which would be here, are sometimes tilted. And it probably wouldn't be enough to simply rotate the entire scene because the flag would wave unnaturally. Instead, we'll incorporate the tilt into our vertex function. We'll need another uniform parameter and we'll call it tilt. So again, I'll open it here and put it over there. It would be another float parameter, so I'll just duplicate this one, Control D, put it over there, and let's call it tilt. And give it a range from 0, because our initial value is just no tilt, just like now. Maximum we'll put to 100, and step can remain 0.1, and default value 0. Okay, now what we need to do is to multiply the tilt by the y coordinate of UV and subtract it from vertex x. So I'll right click here and create another float op, which would be a multiply. As I said, we want to multiply the tilt by the y coordinate of UV, which we have here, it's the green one. And since the bottom part of this tilt would be just shifted to the left, we'll subtract it from the x coordinate of the vertex. So let's add float op, switch it to subtract, and this would be the second argument, and the first one is just where we have it here. This is the x-coordinate. We added this kind of calculation, and just before composing the vector we feed it to this operation and reconnect the result of the subtraction here. Let's check it. Nothing is here, of course, but if we just open the shader parameters and change the tilt, yeah, it is tilting. Can you see? And the rest of the flag is still horizontal. So it looks definitely much better than just rotating everything. Let's put it back and do some more experiments. Speed, it's waving faster. Frequency, changing here, amplitude to make it wave a lot more, or just slightly more, and anything else. So I would say the flag is ready. Now we can add it to some 2D scene and scale it down, so it could work as a nice decoration, especially if we don't forget to add a pole and control the waving parameters from the script. In one of the upcoming videos, we could try a similar effect but in 3D, so the flag would wave in 3 dimensions. Thank you for watching this video, and if you enjoyed it, I would greatly appreciate every like, subscribe, share, comment, and so on. If you want to support my channel even more, you can get my book on game development in Godot 4, which you can currently see on the screen, and the link should be provided in the video description. Have a wonderful time and see you again sometime.